Hi, so let's start a new chapter. So today you are going to learn about rotational motion, and it's from chapter 8 of your textbook. Okay. All right. So in chapter 5, you learn about uniform and non-uniform circular motion. Okay. So while you were learning uniform and non-uniform circular motion, we neglected some quantities called the angular quantities. So here we are going to learn that. Learn those quantities and learn about the rotational motion in details. Okay. All right. So the first thing to understand the rotational motion is to understand that an object undergoes a rotational motion. It basically rotates about some axis. For example, here this object this object rotates about this axis. Okay, so we call this axis at axis of rotation. Okay, so for this object the axis of rotation is O. Okay, now let's consider a point P on this object. So this is the point P on this object, and let's say for simplicity, let's say it's on the x-axis. Okay, so the angle for P, okay, for the point P is 0 now, 0 degree. Okay, although we don't use a degree, I'm going to talk more about that. So the angle of P is 0. Okay, because you see that it doesn't make any angle with the x-axis. Okay, so the angle is 0 here. Now at, let's say this is time at t equal to 0 second. Okay, so time at time t equal to 0 second, the angular position of point P is 0. Okay, now let's say at time t equal to t second, some later. Okay, let's say 1 second or 2 second or some time later, at t equal to t second, the point P is now here. Okay, now you see that it changes its position. So earlier it was here, now it is here. Okay, so it changes its linear position. So this is the linear position, change in linear position, and at the same time you see that it changes its angle also. Now it has some angle. Okay, earlier here the angle was 0 degree 0. Now it has some angle, and that angle is theta. Okay, so this kind of quantity, so we call this as angular position. So angular position. Okay, so now the object's position, I mean the object means the point P's position, angular position is theta. Earlier it was 0. Okay, so you see that very similar to the linear position, we can also have angular position, angular displacement. Okay, when an object rotates about an axis. Okay, now here this L is the this L, I mean the arc length. So this L, this arc length is basically the linear displacement. Okay, because this is the change in the position. Okay, linear displacement, and this theta is the angular displacement. Okay, now from geometry you can determine a relationship between L and theta. Okay, if you know the radius of the path of P. Okay, so the path of P is this one, this dotted circle, and if R is the radius of this dotted circle, then from the geometry, which you probably already learned earlier in math class, okay, the relationship between theta and the arc length, so L is the arc length and theta is the angle, is theta equal to arc length divided by the radius. So this is the relationship between theta and L, and if you simplify it, you can write L equal to R theta. Okay, so this is the relationship between the linear displacement and angular displacement. All right, so earlier you use degree to represent angle. Okay, but in this chapter, when you talk about the angular position, although this is an angle, but we do not use degree. Okay, so remember that we do not use degree as its unit. Okay, so in this chapter, the unit for theta is radians. Okay, in short, we write rad for radian. Okay, so remember that we do not use degree. So degrees are not used here. So we are going to use rad or radians in the chapter to represent the angular position or angular displacement. All right. Now, in linear motion, okay, so if you remember, if something goes in this direction, we use a positive sign. If something goes in this direction, we use negative sign, right? Or if it goes upward, we use positive sign. I mean, our usual convention was something like this. Okay, so similar to that. Okay, so here when you talk about the angular quantities, so our convention is for rotational clockwise rotation, we are going to use negative sign. Okay, so remember that clockwise means negative sign. So you see that clockwise rotation is negative sign and counterclockwise is positive sign. Okay, so for all angular quantities, I mean theta, then later you will be learning angular velocity, omega. So this is not W, it is omega. And this is alpha, angular acceleration. Okay, so for all those quantities, clockwise rotation means negative sign and counterclockwise rotation means positive sign. Okay, remember this convention. Okay, so what is clockwise and counterclockwise rotation? So for example, here this is rotating counterclockwise, so this is counterclockwise. So CCW normally I used to represent this is counterclockwise and CW means clockwise. Okay, so you see that it is normally clock rotates in this direction, right? So here, because the rotation is opposite to the clockwise, okay, so it is counterclockwise. So for counterclockwise we use positive sign, for clockwise we use negative sign. Okay, so this is our convention. All right, now the next thing we are going to learn is relationship between theta and degree. Okay, so as I said that we are not using degree to represent theta here. We are using radian, but what is the relationship between degree and theta? Okay, so here is the relationship between degree and theta. Okay, so let's say this is the okay, so this is the coordinate system. So it starts from here. Let's say we have an object. Okay, so this is the object and this rotates about this axis, so the origin. Okay, and let's say it rotates a full circle, okay, full turn and come back here. Okay, and let's say this is the radius of this path is r. Okay, so when it travels the whole circle, one full turn, you know that the L, okay, the linear displacement, so the linear displacement is this one, right? So linear displacement is the circumference or perimeter. Okay, and that is equal to 2 pi times the radius, right? And theta is what? So you know that this is 90 degree, this is another 90 degree, this is another 90 degree, this is another 90 degree. So when an object travels the whole circle, okay, for one full turn, it basically travels 360 degree, right? For one full turn, it travels 360 degree. Okay, now let's use our usual definition of theta. So theta equal to L over R. So L is 2 pi r for one full circle. Okay, for one full rotation, it is 2 pi r. and then r, and for one full rotation the theta is 360 degree. So you see that r and r cancel out, and here 2 pi is equal to 360 degree. Okay, so as 2 pi is equal to 360 degree, 1 radian, so that is basically 2 pi radian equal to 360 degree. So 1 radian is 360 degree divided by 2 pi, and that is equal to 57.3 degree. Okay, so this is the relationship between radian and degree. So 1 radian equal to 57.3 degree. Okay, all right. All right. So similar to the linear displacement, we can have angular displacement. For example, let's say at time t equal to 0, it is let's say we have a point P here. Okay. So let's say at t equal to 0, the point P was here. And now at, let's say at t equal to t1, okay, the object somewhere here. So the theta is theta 1. Okay, now let's say at time t equal to t2, okay, the object, the point P is now here. Okay, so the angle earlier it was theta 1. Okay, and now this is the angle theta 2. Okay, so theta is now theta 2. Okay, so the change of the angle between t1 and t2 is delta theta. So delta theta is the angular displacement. It is the final angle minus the initial angle. So the final is theta 2, initial is theta 1. So this is the change in the angular position, and change in the angular position is the angular displacement. Okay, it's very similar to the linear displacement that you learn in chapter 2. Okay, all right. And similar to the position, linear position and the linear displacement, the angular displacement unit is also radian. Okay, all right. The next we are going to learn about angular velocity. Okay, so similar to the velocity, we can define also the angular velocity. For angular velocity, we use this symbol omega. Okay, so this is omega, it's not W. It's a Greek symbol, we call it omega. Okay, and it's basically the lowercase omega. Okay, so omega is, so if you remember, the velocity or the average velocity was the change in position with respect to time. Okay, so the angular velocity, the average angular velocity is the same thing, the change in displacement with respect to time. Okay, you see that this is the definition. Okay, and the instantaneous angular velocity is omega when delta t is very small. Okay, very similar to the instantaneous velocity. Okay, all right. Now it's a vector quantity similar to the velocity. It's again a vector quantity because it is a velocity, and the convention here we use is counterclockwise. So similar to the displacement and the position, counterclockwise is positive sign, clockwise is negative sign. Okay, and the standard international unit is radian per seconds or rad per second. Okay, so radian for theta, time for second. So the standard international unit for angular velocity is rad per second. Okay, all right. The next thing is the angular acceleration. Similar to the acceleration, linear acceleration, we can define the angular acceleration. For angular acceleration, we use the symbol alpha. So this is another Greek symbol. We call it alpha. Okay, so the average acceleration is this change in omega with respect to time. I mean, changing the angular velocity with respect to time. Okay, and it is final velocity minus initial velocity divided by time. Okay, and the instantaneous angular acceleration is this one when time is very small, delta t tends to 0. Okay, and the standard, again, it's a vector quantity similar to the acceleration. The standard international unit is radian per second square. Okay, so it is radian per second for velocity. For acceleration, I mean for angular acceleration, is radian per second square. So remember that for linear velocity it was meter per second. So here we have radian per second. So omega is rad per second. For alpha, I mean A, we had meter per second square, and for alpha now we have rad per second square. It's very similar. Okay, all right, and convention for alpha is similar to all other angular quantities. That means clockwise is positive. I mean clockwise rotation gives us positive sign, and sorry, counterclockwise rotation gives us positive sign. Clockwise rotation gives us negative sign. Okay, all right. Now the relationship between the linear and angular quantities. Okay, all right, so the first one is the v and omega. Okay, so earlier we see a relationship between L and theta, right? L and theta was L equal to R theta. In the last slide you already see that, right? And that you can determine by using just the geometry. So the arc length equal to radius times the angle. Okay, that you already see. Now we are going to find a relationship between the linear velocity and angular velocity. So a relation between v and omega. Okay, so to do that, okay, let's start from the definition of linear velocity. So linear velocity here is delta L delta theta. Okay, so normally we use, I mean in chapter 2 we use delta x delta t, right? For v we use delta x delta t, but because in this, I mean now our object is moving in a circular path. Okay, and the linear displacement here is L. Okay, so you see in the last slide the linear displacement is L. So instead of x we use L. Okay, so let's start from this equation. The linear velocity is equal to change in linear displacement. So this is not theta, this is t, right? Delta t. So delta L delta t, rate of change of linear displacement with respect to time. Okay, now delta L is, I mean L is r theta, right? We can write that, and r is radius, which cannot, I mean we cannot change the radius, right? So because r is constant, we can take this out of delta. Then our equation is something like this: delta theta delta t, and delta theta delta t is omega, right? So you see that v equal to r omega, very similar to L equal to r theta. Okay, so this gives us relationship between velocity and angular velocity, I mean the linear velocity and angular velocity. All right, now the next thing is the relationship between acceleration. Okay, now we have two types of acceleration. One is when an object is moving in a circular path. Okay, let's consider just the non-uniform circular motion, non-uniform circular motion. Okay, I've already discussed this earlier in chapter 5, so I'm not going to discuss this. Okay, so in a non-uniform circular motion we have two types of acceleration. One is centripetal acceleration, right? Centripetal acceleration was AR, that was equal to V square over R, and another is tangential acceleration. Okay, and tangential acceleration was A tan, that was equal to delta V delta T. Okay, so it's just a general case where the motion is non-uniform. Okay, so if the motion is non-uniform, we have two acceleration. One is centripetal acceleration. Centripetal acceleration direction is to the center. Okay, and tangential acceleration direction is tangent to the to the circle. Okay, at any point of the circle. So because we have two acceleration in any non-uniform circular motion, so we have, I mean, we should have two relation between this and this with the angular quantity. So now let's try to determine the relationship between A tan with some angular quantities and AR with some angular quantities. Okay, let's see what we get. Okay, so the first, let's start with the tangential acceleration. So the tangential acceleration, which I just erased, is this: A tan equal to delta V delta T, right? And V, earlier we determined that is equal to R omega, right? R is the radius, so it's a constant, we can take it out. Okay, so we have something like this. So what we get here is R alpha, because rate of change of the angular velocity with respect to time is the angular acceleration. So what we see here, A tan equal to R alpha. Okay, so you see that we have L equal to R theta, we have V equal to R omega, and now we have A tan tangential acceleration equal to R alpha. They are very similar. Okay, on the left hand side we have linear quantities, on the right hand side we have R and then the angular quantities. Okay, so these three relations are very similar, but the centripetal acceleration is a little bit different. Okay, so let's try to determine the relationship between the centripetal acceleration and angular quantities. Okay, so if you remember, the centripetal acceleration is this V square R. Okay, now if I substitute the expression for V, so the expression for V is this, so it will be R square, I mean R omega whole square R. Okay, okay, so it's R square omega square R, so one R cancel out, so AR, the centripetal acceleration, can be written as this. So AR equal to R omega square or omega square R. All right. So this table shows the relations. Okay. Now the next thing I'm going to show you is the relationship between angular quantities and the frequency we learn in chapter 5. Okay, so in chapter 5 we derive two equations, okay, for velocity. So V equal to 2 pi R over T, and from that we see that it is 2 pi R F. Okay, so here R is the radius and T is the time period, F is the frequency. Okay, so if you forget the concept of this, please go back to chapter 5 and review it again. Okay, but this we already discussed earlier. Okay, now I want to know what is the relationship between the this frequency with the angular quantities. Okay, So to know that, let's start from this equation and substitute V equal to R omega. Okay, so what we get is this. R cancel out, so we get a relationship between omega and the frequency, and this is this. Okay, so because omega is 2 pi f, 2 pi times the frequency, sometimes this angular velocity also called angular frequency. Okay, angular frequency, especially in chapter 11 we'll be calling it angular frequency. Okay, but if you call it angular velocity, it's also okay. Okay, normally in this chapter we call it angular velocity. In chapter 11, the same quantity, okay, we call angular frequency. Okay, because of this relation. All right, the next thing we are going to I'm going to talk about the kinematics equation. Okay, so in chapter 2 we learn about 4 equations. Okay, so when an object travels in a straight line at constant acceleration, that motion can be expressed by using 4 important equations. Okay, and those 4 equations are, let me write down here, that 4 equations are these. X equal to x0 plus v bar t. The second equation was v equal to v0 plus at. The third equation is x equal to x0 plus v0t plus half at square. And the last equation was this. Okay. So we learned this and used these 4 equations several times earlier, right? Now, similar to these 4 equations, for linear motion, we can write 4 equations for angular motion, okay, rotational motion. So what we have to do, we have to replace x by theta. Okay, that means x0 to theta 0. Okay, v by omega, v0 by omega 0, a by alpha. Okay, so if you replace all these by the angular quantities, all the linear quantities by the angular quantities, without knowing a lot of detail, we can write the 4 equations, okay, for the rotational motion. And those 4 equations we call the kinematic equation for rotational motion. What are those 4 equations? So these are the 4 equations. Okay, so these are the 4 equations. Okay, 1, 2, 3, 4. Okay, so here you see that I replace x by theta, x0 by theta 0, v by omega, v0 by omega 0, and a by alpha. Okay, that's it. So we get these 4 equations. Okay, now let me erase this and just focus on these 4 equations for the rotational motion. Okay, so here one thing is not that important, is the initial position. So initial position for linear motion was x0, initial position, right, x0. And in many problems we use x0 equal to 0 meter. Okay, so our reference was x0, so we use, most of the time we use x0 equal to 0. So here we also do the same thing, theta 0 equal to 0 for most of the time. Okay, 0 radian. Okay, so because theta 0 equal to 0 radian most of the time, we are eliminating theta 0 from the equations. Okay, so if you eliminate these, it becomes this, theta equal to just omega bar t as we don't have theta 0 here, it's basically as is. And you eliminate this, the equation now becomes this. Okay, and here you eliminate this, your equation becomes this. Okay, so these are the four equation, and these four equation we call the kinematic equation for rotational motion. Okay, and again, these kinematic equations are only valid when the objects are moving in a circular motion. I mean, when the object rotates at some constant angular acceleration. So alpha needs to be constant, similar to A is constant for linear motion. Okay, all right. All right. So as the angular velocity and acceleration are vector quantity, there should be some direction. Although here I'm not going to discuss all the details. Okay, as we already use some convention. The convention we use, I mean, so clockwise means negative and counterclockwise means positive, right? Counterclockwise positive, counterclockwise rotation means positive sign. Okay, so these are the convention, these are not the direction. Okay, now what are the direction? So direction can be determined using the right hand rule. Okay, now we are in algebra based course, we do not much interested on the direction of the angular quantities, so I'm not going to discuss this. Okay, so we need right hand rule to discuss the direction of the angular velocity and angular acceleration. Here I'm not teaching this. So for algebra based course, you just need to understand that clockwise rotation means negative sign and counterclockwise rotation means positive sign. Okay, that should be enough. All right, now the next thing is the rolling motion without slipping. Okay, so now rolling without slipping depends on the static friction between the rolling object and the ground. Okay, the friction is static because the rolling object's point of contact with the ground is at rest at each point. Okay, so here we are going to discuss about rolling motion. Okay, so here I'm not going to discuss about the math. When we talk about, when we solve some problem, we'll see this again, and then it will probably help you to better understand. But for the time being, let me just talk about the physics of rolling motion. Okay, so rolling motion involves when you ride a bike. Okay, so you know that when you ride a bike, the wheels undergo rotational motion, right? And at the same time, you move forward. Okay, so that means we have also translational motion or linear motion. So rolling motion basically involves both translational motion and rotational motion. Okay, so when you combine both together, it gives you rolling motion. But the thing is, to have rolling motion without slipping, there should be sufficient static friction between the contact point of the wheel and the ground. So here there should be sufficient static friction. Okay, if there is no if the static friction between the wheel and the ground is not enough, then it will not be rolling motion, it will be something else, it will be sliding. Okay, so you know that if you try to drive or ride a bike in a icy ground, okay, you know that it is very difficult to do that. Okay, to drive a car on an icy road, right? So that's because there is not enough static friction between the wheel and the ground. Okay, so the physics of that is different, and this is a little bit complicated, so we just focus here when there is sufficient friction between the wheel and the ground. Okay, and that is the static friction. So you may have the question that the bike is moving forward, so why not it should be kinetic friction, why it is a static friction? Okay, so to understand that, we have to go to the next slide. Okay, for the time being, just remember that the the friction between the wheel and the ground is static friction. If there is enough static friction, then it should be rolling motion without slipping. If not, then it will be sliding motion, which we are not interested here. Okay, so here I talk about the center of mass little bit, but you already know from the last chapter. In chapter 7, we already talk about the center of mass. So I'm not going to talk it here. Okay, so let me come back to here. Okay, so rolling motion is combination of translational and rotational motion. Okay, so that I already mentioned in the last slide. Okay, so here you see that we have translational motion. In translational motion, all the part of the wheel has the same velocity, same linear velocity, v. Okay, so you see that is v. Okay, in translational motion, we can think the object as just a point object. Okay, okay, or we can think that the center of mass of this object, because it looks like a uniformly distributed object, and we can think that the center is we can think that all the mass is concentrated at the center, so we can think that the center is moving with the velocity v. Okay, so in translational motion, the thing is all parts moves or travels with the same velocity v, same translational velocity v. Okay, and you see that. Now in rotational motion, okay, so let's say the object is moving in a clockwise rotation. Okay, so if it moves in a clockwise, so it will be going okay, it will be something like this. So in clockwise rotation, okay, the direction of the linear velocity, so remember that linear velocity v relates the angular velocity with linear velocity with the angular velocity by this equation, right? V equal to r omega, where r is the radius. Okay, all right. So now in rotational motion, okay, let's say this, let's consider this second part. Okay, let's say this object is rotating about this rotational velocity omega. Okay, now if it is rotated with this angular velocity or rotational velocity omega, then at this point, okay, the velocity, because it is moving in this direction, the linear velocity v will be this. Okay, v equal to r omega. So v is always tangent to the, where in rotational motion, so if I want to know what is the v at this point, it will be tangent to that point. Okay, and as you know that v equal to r omega, so at this point, so okay, so here r means big R or omega r, so at this point the velocity will be r omega. At this point it will be again r omega. Okay, but you see this time the direction is different. At this point it will be again r omega or omega r, but here we use a negative sign because the direction looks like negative x. Okay, and so on. Okay, and rolling motion means the combination of these two. Okay, now if we understand this, okay, then first let's look at this simulation and come back here. Okay, so you see that v1 is a pure translation. So pure translation means it's moving something like this with the same same velocity v. Okay, Okay, so what I wanted to show you is not this. So this is the translational velocity. Okay, so this is the translational velocity. I mean translational motion, pure translational motion. Now I want to show you yeah. So this is pure translational motion. Okay. So you see that all the points are moving at the same velocity, same translational velocity v. Okay. Now, next, what I want to show you is this one. Okay. So here you see that the blue, so look at how it is moving. Okay. So here blue means the translational velocity. Okay. So you see that there is no change in the direction of the blue. Okay. It's always in this direction. So blue is always in this direction. Let me use blue for blue. Okay. So blue is always in this direction. There is no change in the blue. Okay. And this blue means the translational motion. Okay. On the other hand, you see that the green is always changing. So blue is v. I mean blue is because of translational motion, and green is rotational due to rotational motion. And you see that green arrow is always tangent to the circle. Okay. So green arrow is always tangent to the circle. And red is the combination. So because velocity is a vector quantity, so we have this velocity, okay, due to the translational motion, and this velocity due to the rotational motion. The red is basically showing us the net velocity at every point. Okay. Now the thing I want to show you here is okay. So you see that at this point, okay, at the top point, you see both the green and blue are in the same direction. Okay, so both green and blue are the same direction, so they added together. So here green and blue are both in this direction, so they added together, and you see the length of the red arrow is now double of green and blue. Okay, so you see that here. Okay, at the top point they add together. Now if you look at this point, when it comes to the contact between the wheel and the ground, you will see a different thing. So here you see that at this point, when the wheel is in contact, I mean this point is in contact with the ground, you see that the green and blue are opposite to each other. Okay, so because the green and blue are opposite to each other, the net velocity is 0 at this point. Okay, so net velocity is 0. Okay, so net v equal to 0. So when v equal to 0 means that point is at rest. Okay, in many problems you see that when the object is at rest, the velocity is equal to 0. So for this point, okay, when the point that is in contact with the ground, the velocity of that point is 0. Okay, and we know that the static friction, we have static friction when the object is not in motion. Okay, so this point is not at motion, so that's why we have the static friction here. Okay, now let's go back to the slide, and you see the same thing over there. Okay, so you will see the same thing here. Okay, so here you see that at this point they added together. at the top they added together, and at the bottom this is 0. Because the net velocity is equal to 0 here, the friction between the wheel and the ground is static friction. Okay. All right, so we'll be doing at least one problem in the problem solving class. Okay. Now let's talk about the torque, and that's it. That is the last thing for today's lecture, and we have few more things that we will be learning in the next lecture. Okay. All right. Now torque is very similar to the force. Okay. So we already see that for a linear displacement we have angular displacement. For a linear velocity we have angular velocity. For a what I wanted to say here, we already see that we have linear displacement, angular displacement, angular velocity, and angular acceleration. Okay. Now similar to that, we already learned about the force earlier, right? So similar to the force, we have a angular equivalent of force that we call torque. Okay, so torque here that we are going to learn, this is basically angular or rotational equivalent of force. Okay, so this is rotational equivalent of force. So when we have rotation, for example, something like this, look at these two pictures. Okay, this and this. So here rotation involved, and because rotation involved, the concept of torque we can apply here. Okay, so let's first learn what is torque and then try to relate how torque is involved here in this rotation. So remember that the first thing we should remember is torque is involved when rotation is when there is some rotation. Okay, so when there is rotation there is torque. Okay, and rotation and the torque is the rotational equivalent of force. Okay. All right, so to understand torque, let's consider a door. Okay, so let's try to open this door. Okay, so the door rotates about this axis. Okay, so this is the axis of rotation. Okay, so this is the door, the top view of the door, and this door can open or close about this axis. Okay, so this is the hinge of the door, and we can open or close. We can rotate this door about this axis. Now to open the door, what we have to do? We have to apply some force. Okay, it's just a linear force. Okay, the force that we learned in chapter 4. So where should we apply the force? We can apply the force here, right? Here, or anywhere, right? We have the choice. Now the thing important is where which force is more efficient. For which force we can efficiently open the door. Okay, I think your answer is this one, right? So from our common sense, from our everyday life knowledge, okay, it says that if we apply a force here, the door will be easily opened. Okay, we can easily rotate the door if we apply a force here. Okay, so you see that to understand torque, the first thing we need to understand is rotation is involved. Rotation involved means the object is rotating about some axis. So this is the rotation axis, and then the next thing is we need a force. Okay, and force needs to be applied somewhere so that we can efficiently rotate the object, right? So the point where force is applied, okay, and the axis of rotation, the distance between the axis of rotation and the point where the force is applied, we call that distance as lever arm. Okay, so for this force we call this is the lever arm. For this force we call this is the lever arm. So the lever arm here in this the first picture is RA or RB, and we see that when the lever arm is RA, we can easily or efficiently open the door, right? Now let's look at the next picture. So here it gives some information. It gives us that to have, to understand torque, we need to know that whether the object is rotating or not, and what is the axis of rotation. Okay, so the axis of rotation is important first, and then where the force is applied. Okay, so we see that if we apply the force somewhere here, we can rotate the door efficiently. Okay, so from that we define a quantity called lever arm, and lever arm is the distance from the axis of rotation to the point where the force is applied. Okay, now let's look at the next picture. The next picture, we apply the forces at the same point, at almost the same point. So the lever arm for all the forces here is RA. But you see that we can apply forces in different direction. Okay, and from our common sense or the everyday life experience, we can see that this is more efficient, right? When we apply the force in this direction, we can open the door efficiently. We cannot even open the door if we apply the force in this direction, right? So this is less efficient. Okay, FC is okay, but it's not that efficient as FA. Okay, so what we see here is the axis of rotation is important, the lever, the force is important, the lever arm is important, and also the angle between the lever arm and the force. Okay, so few things we need to understand torque. Okay, so when you combine all these, okay, then the mathematical definition of the torque becomes this. Okay, that for torque we use the symbol tau. Okay, so this is called tau, is again a Greek symbol, tau. So R is the lever arm, F is the force, and theta, sine theta here, theta is the angle between the lever arm and force. Okay, so torque is involved when there is rotation, and torque is defined by using this equation where R is the lever arm, F is the force, and theta is the angle between R and F. So for example, let's say this is the axis of rotation. Okay, and this is the lever arm. So you apply a force here in this direction. Okay, so this is the force. Okay, now what is the theta? Okay, so we know this is the lever arm. Lever arm is the distance from the axis of rotation to the point where the force is applied. Okay, so this is the lever arm, the force is applied here, so this is the force. Now what is the angle? So I said that theta is the angle between R and F. Okay, and then it could be this angle, or you can extend R. Okay, and you can make an angle between the extension of R and F. Okay, so no matter which angle you use, either this angle or this angle, it would be the same mathematically or numerically, it will be the same. Why? Because in trigonometry there is an identity called sine theta equal to sine 180 degree minus theta. Okay, so because of this trigonometric relation, no matter which angle you use, either this angle or this angle, you should get the same numerical value. Okay, all right. Now once you have this information, the few more thing you need to understand is it's a vector quantity. The standard international unit is meter Newton. So meter coming from R and F, Newton coming from F. So when you combine this, the standard international unit for tau is meter Newton. Okay, and similar to all other quantities, clockwise rotation means negative sign and counterclockwise rotation means positive sign for torque. Okay, and as I already mentioned, torque is the rotational equivalent of force. Okay, so I'm going to stop here. In next lecture, we are going to learn more about, some more about the rotational motion.